In elementary school, the principals are more your pals. R. R is the annual interest rate.
Yearly?
Yep. They'll say annual interest rate, and it has to be as a decimal. N is the number of times compounded per year. The number of times compounded per year. So monthly is how many times a year? 12. If I said quarterly, how many times a year is that? Does anybody know? 4. Okay. If you're not sure, ask me. How many times a year is that? All right. Then T is the number of years. Now, notice. Remember how before we did, for B, we did 1 plus or 1 minus? The 1 plus is already in the formula for you, so don't do it twice. Don't do 1 plus 1 plus. It's 1 plus because it's a growing thing, but it's interest. Interest is growing. Okay, so that's why it's 1 plus. All right, let's pick some things out here. It says, suppose your parents deposited $1,500. What thing is that in the formula? Yep, the principal. At an account paying 3.5% interest, compounded annually. Annually is once a year. Write an equation for this problem. All right, let's do it. A equals, A is the amount, A for amount, equals the principal, which is $1,500, 1 plus R. R has to be written as a decimal. What's R as a decimal? 0.035 divided by N. Annual is once a year. So I'm going to write once. So we're going to divide it by 1. Okay, do I really need it there? No. I'm going to write it down just so you understand that annual means once a year, but we don't really need it there, okay? Because dividing by 1 isn't going to change anything. All right, and then I'm going to put time times 1. I put time times 1 because that's my general equation, okay? That will do for as many years as I would like. But I ask you to do this for 18 years. So you're going to want to use parentheses on your calculator, and just do it with me a second. We're going to do 1,500, and then we're going to do 1 plus 0.035. You could do the divided by 1 if you want. We're going to do, won't need to. And then we're going to do to the power. The power is the caret key. Looks like this. And we wanted to do to the 18th power, correct? So after 18 years, there would be $2,786.23 in the account. Okay, what I'm going to show you is why it's better if interest is compounded more often. Okay, so I'm not going to change anything in the problem except I'm going to change how many times a year you get the interest. So this next time, we're going to write an equation for the problem. We're going to find the balance after 18 years. If the interest was compounded quarterly, what does that change? What letter? Just the N. Yeah. Okay. So it would look like this. A equals 1,500. Quarterly is 4 times a year, so we're going to do 1 plus 0.035 divided by quarterly, 4. And then it's T times 4. So notice it's N is in 2 spots. Because what's happening is you have to do this 4 times a year. And so last time it was just once a year, whammo, once. This time I have to do a little bit spaced. It's not like you're taking 3.5% every quarter, but that 3.5% you get a little bit, and so when you get a little bit, they put it in your account. So now your amount's a little bigger, and you're going to make a little more interest because it's on a little bit more of an initial amount. Let's plug it in for 18 years. By the way, 18 times 4 is 72. So when I do this, it's going to be 1,500 times 1 plus 0.035 over 4 to the 72nd power. Because 18 times 4 is 72. 18 is T. 18 times 4 is 72. All right, let's type it in. I got $2,808 and 71 cents. 70 cents. All right, now, what do you notice about this number compared to A? Yeah, it's a little bit higher. It's a little bit higher because that interest you got a little bit more often. You still got it for 18 years, but you got a little bit broke it up, and then what happens is once you get that interest, they put it back in your account. So if you're finding a percentage of a higher number, the final outcome is going to be higher. What do you think is going to happen when I move it to monthly?
It'll go down.
Well, quarterly is 4 times a year, monthly is 12. Going to go a little bit higher still. All right, let's set it up. 1,500. We're going to do 1 plus 0.035 divided by 12. Good. And then to the T times 12 power. So hold on a second. Let's figure out what 18 times 12 is. 216. So when I type this in my calculator, I'm going to do 1 plus 0.035 divided by 12 to the 216 power. Okay. And I get So if the only thing you change is how often you compound something, the more that you compound it, you're going to get a little bit more money because you're getting your interest more often. Okay? Okay. We have just enough time to talk about half-life. So, in a half-life problem, here's the deal. Half-life D, what's the D value, do you see? Half. It's always half. Because we're trying to figure out how long it takes to get that half. What do you think A stands for? Initial amount. And then what happens here is we change the power around. We actually take X divided by the HL. And the HL is the actual half-life. And so I'm going to talk about this a little bit more tomorrow, but I want to just show you in general how it works. This is a medical application, half-life is used to find out how long, like, you would have a medication in your body, because you would want to make sure the medication completely was out of your body before you gave it another appropriate dose. So it says the half-life of a radioactive substance is the length of time for half of the substance to decay. To treat some forms of cancer, doctors use radioactive iodine. The half-life of iodine-131 is 8 days. By the way, that 131 has nothing to do with the problem. If you ever took chemistry, they have sometimes numbers behind chemicals because there's different concentrations. So iodine-131 is the name of it. You're not going to have a 131 in your problem. Okay? A patient receives 12 millicuries, a treatment of 12 millicuries. What would 12 represent in our equation? A. So let's write an equation. Y equals what am I going to write? 12 times 1/2 or 0.5 to the x divided by, what's the length of the half-life? So to the x divided by 8 power. That's your general equation. It says, find out how much iodine is left in the patient 16 days later. So if I put 16 in for x, what would the power be? 2. Isn't 16 divided by 8 2? Okay, so let's find out 16 days later how many millicuries of the treatment are left. Can't we do this in our heads? How many times am I taking a half? Twice. Okay, 12 times a half is 6 times a half is 3. If you want to verify with your calculator, you can. But there should be 3 millicuries left after 16 days.